behalf of the organizing committee, I welcome you all to the conference talk. I'm sure you will enjoy it.
So welcome everyone. Thanks for coming to this conference. So we'll begin our session. So the first talk will be by Professor Ronnie Sircar from Princeton University. And it's our privilege that he made all the way up to here. It's his first time in Chennai, so please welcome him. And it's really a nice opportunity to listen a talk from him on energy prices, dynamic Millfield games, and stochastic demand. So I'll just invite him without further delay.
Okay, so thank you, Intronil, for the introduction, and thank you to the organizers for inviting me and putting on this, what looks to be a very nice and interesting conference, and it's very nice to be in Chennai for the first time. So, as Intronil mentioned, I'm going to talk about some models which are related to energy markets, commodity markets, production of energy from different fuels, and in particular, they use certain developments in dynamic game theory, which I'll try and sort of introduce from the beginning and sort of explain how these things develop and can be applied to this situation. So So I've been interested in these game theoretic models for a number of years. I'll just get some chalk. In fact, going back to when I was doing a master's degree in England some years ago. And so in these models related to game theory, they're more closely connected to mathematical economics. And here we're really talking about how prices and, for instance, volatility are dictated by supply and demand, and when there's a large number of players, or a small number of large players who have an influence over how a market evolves. So I started with this in my sort of master's thesis, and then that work didn't become a paper until a full 16 years later. Not that we worked on it all the time, but there were gaps and delays, and eventually we got around to finally completing that, though it also took a long time. And since then, since that first paper was completed, I've been interested in this subject for the last 7 or 8 years, and I'll describe some of that work. In the meantime, I had been more involved in models related to finance. And in finance, as you've seen in the introductory lectures, and you'll see in the talks in this conference, there we usually think of the model for the price as the given thing. So you typically will write a stochastic model for price. That's the model. You write how stock prices or how commodity prices developed over time, and then investors, market participants, are not really influencing that model in typical, at least first order models that we use for option pricing, for portfolio optimization. So these players are typically price takers. Whereas now, going back to the situation that I want to talk about here, the players are influential. They're not, they don't observe the price and leave it unaffected. They very much determine the price by their actions. So here is essentially the setup. Typically, you're interested in a type of a market with a number of competitive and influential producers, a so-called oligopoly. And typically you have a finite number of these n, but the mean field theory is to make that n equal to infinity. The way competition is resolved just by choice is through Nash equilibrium or game theory. And historically there have been two extremal models of competition: Cournot markets, in which firms set quantities, and Bertrand markets, in which firms set prices. So Cournot arguably was the first person to look at these kind of models. He wrote a book in 1838. And when people say Cournot models, they mean that the control variable, the thing that firms decide or the players decide, is how much of a good to produce. And then the price reacts to the quantity. What's commonly known, and what I'll also use this terminology as Bertrand models, is that the players set a price for their goods, and depending on the price they set, people will buy more or less of that good. Now, this naming, as you know from in any field, naming is always a very inexact science. It turns out that Cournot in his book had both quantity setting models and price setting models. Bertrand didn't have a paper, he had a book review, a review of this book some 50 years later, and he was very critical of the book. But a later analysis of this book review reveals that Bertrand didn't really understand the book. But just historically, people have thought that Bertrand criticized Cournot's work because he set quantities, and therefore someone later, a few 20 years later or something, Edgeworth maybe, attributed to Bertrand models in which the price is set. But historically, it's actually Cournot had both, and it should be called Cournot in quantity or Cournot in price, but it's too late now. As you know, these misnomers stick, and I'll also refer to this as Bertrand. But Bertrand actually shouldn't, Bertrand gets credit for something else, but not actually for this, this contribution to game theory. But anyway, these are the two extremes. And over the years, people debated, which one is the right model. And of course, that's not the right question, because some markets, for example, production of oil, quantity setting is more natural, whereas in other markets, for example, consumer goods, televisions, things like that, computers, the Bertrand model is more appropriate. So these were models in one period. We play a game and then it's over and we go home. But of course, things change over time. They may change over time uncertainly, in which case games become stochastic. And so when you look at the continuous time versions of this game, these games are non-zero sum, and these are notoriously difficult to solve, even numerically, let alone just be able to say anything mathematically about them. So what I want to sort of try and describe is, if we think of the number of players as being in a continuum, this is the continuum mean field game approximation, then there is some progress that one can make in that situation. And what happens in the kind of games that we're interested in is that the players are asymmetric. They're not identical copies of the same players, so this asymmetry plays a role. And secondly, as you'll see in the situations I'm interested in, players may disappear from the market because the market becomes too expensive for them to participate in. So you may start with a market with n players, and one may drop out. You'll have n-1, and this may go down all the way towards a monopoly. And I'll describe the situation I'm thinking of where this kind of thing happens. And please interrupt me with questions. Don't save them to the end. Save them to the end as well, but please feel free to interrupt if something's not clear. So just to set a scenario that is related to the Cournot type model, even though largely I'll be talking about Bertrand just to describe the subject, there is this situation with oil prices that you will probably have read about, since it's still a sort of an ongoing situation, which is that there has been a steep decline in the price of oil from over $100 a barrel in June of 2014, which is up here, to as low as $28 a barrel in April of 2016. Currently has recovered a bit to about $60 a barrel, but this is an drop. And not only that, against most predictions, it's a sustained drop. It has stayed low for the past 3.5 years, at least relative to this situation. And one reason, or the reason that people largely attribute to this decline, so for a number of years it had been above $100 a barrel, and people had predicted, experts who had studied oil for much of their career had predicted that that's the new normal. Oil will always be above $100 a barrel, but it has not been, at least over the last 3.5 years, and that's largely due to increased production of shale oil in the United States, which itself arose from this fracking technology, which allowed oil producers to reach oil and natural gas that they were not able to reach before in states like Illinois, North Dakota, and Texas, and Oklahoma, and other places. And so that's an increase in supply. Suddenly, the US was producing a lot more oil, and the same thing happened in the natural gas markets a few years earlier, and an increase in supply led to a decrease in price. And that is a Cournot type thing if you view the oil market as a competitive market, that suddenly the quantity increased from one of the players and the price went down. And then in this sort of game theoretic or strategic way of thinking about things, people expected OPEC, the coalition of Middle East oil producers and others, mainly dominated by Saudi Arabia, that they would want the oil price to go back up because their economy depends on a oil price above $80 a barrel for various reasons, and their strategic thing would be to reduce production, and therefore the price would go up. This is really Cournot. You cut the quantity, the price goes up. But in fact they didn't. It surprised a lot of people. In November 2014, up until about November of 2017, they decided not to do that. It's only recently that they have decided to do that, and the price has kept up recently. So one of the goals of these type of models is to try and understand the strategic reason for doing that. Their argument is that they wanted to keep their market share, and that producing oil from fracking technology is much more expensive, and therefore those firms would go out of business. And some of them have, but a lot of them have not. So this is just to motivate that this, at least in this kind of a context, even though I'll not come back to this application so much in this talk, is a situation in which you have competition, in which you have Cournot competition, and you have potentially a number of very influential players, the fracking producers in the United States, OPEC, Russia, there are others that you could put into this situation. Okay, so what is the, how do these, let me sort of develop these models in a sort of systematic way. So I'll focus on Bertrand competition, but I'll mention as a fact that in the continuum limit of the mean field game, Bertrand and Cournot are actually the same model. Not when the number of players is finite, they're very different, but in the limit they're exactly the same. So in these situations, you have a player I, and he or she is trying to maximize profit pi I, and profit is given by quantity multiplied by price minus cost. So each player will have a per unit cost of production. In oil, this is relatively expensive for fracking. It's relatively cheap for Middle East producers of onshore oil. It's relatively expensive for solar and wind if you consider renewable energy. But each player is distinguished that if he or she produces QI units of energy, say, then the cost is QI times SI. So SI will distinguish the costs of the players. And each of the players is revenue maximizing. So if he or she produces QI units of energy, then this is the revenue that they get. And the Cournot model is that I give you a function, a pricing function or inverse demand function, and the price that player I gets is a function of the vector of quantities produced by all of the players. So the model is, given this function, or these functions pi, what is the price given the quantities produced? The Bertrand is the inverse of that, that given the vector of prices p, what is the demand, how much does player I manage to sell? So that's a demand function. So D is a direct demand function, and P is an inverse demand functions. And so in earlier work, we had looked at sort of the n-player version of this in continuous time, where each player would have, if you'd look at it through dynamic programming, will have a differential equation of its own, and these are notoriously difficult to solve, as I had mentioned earlier. You have a system of differential equations, and you have one differential equation for each of the players. The continuum mean field game approximation, which was developed about 10 years ago in different contexts by Lajoie-Lyons and Huang Malamé Keynes. In this approximation, as you'll see, there are actually only two equations to deal with, and at least computationally, that makes the situation a lot more tractable computationally. Okay, so let me continue with how the story developed. So there is a distinction between markets where you have homogeneous goods. The goods are all identical, and so there is only one price. So if you look at the typical Cournot game with homogeneous goods, then each player is solving a problem like this, is to maximize the revenue, which is the quantity, and then the model, so the models that I'll use typically are of the form 1 minus the quantity or the average quantity, depending on the situation. So here, the pricing function is 1 minus the average quantity produced by all of the players minus the cost. So the pricing function is, is 1 minus quantity. There are other ones I'll talk about at the end, but just to keep things simple, I'll work with this situation. Now, what the continuum approximation is to say that there's an infinite number of these players, and you replace the sum or the average by the integral of the players with some density here. And so now, for a representative player, he or she is maximizing this quantity here, but this Q is inside an integral, so it only has an infinitesimal effect on this average. And so this maximization problem is just to the answer to this is either 0 or infinity, which is not really a useful limit in the continuum sense. So for many years, we were not so interested in this mean field game thing because it didn't make sense for the homogeneous good situation. On the other hand, if the goods are homogeneous, meaning they're absolutely identical, meaning a barrel of oil here is the same as a barrel of oil in Oklahoma, then the Bertrand-Nash equilibrium is sort of wrong in the sense that what it tells you is that if you had the Bertrand model and you pretended that all of the players produced identical goods, then the Nash equilibrium in the Bertrand sense is winner takes all, which means whoever has the lowest price gets all of the demand. And that, you don't see that happening. A typical example is Coca-Cola versus Pepsi, that even if one is cheaper than the other, some people prefer one over the other, and it's not just the person who produces the lowest price gets all of the demand. And so for many years, the Cournot versus Bertrand debate was that Cournot gives the right answer with the wrong model, that for consumer goods, for instance, then Bertrand gives you a crazy answer. The competition is too strong. It's just whoever has the lowest price gets all of the demand. Cournot doesn't give you that answer. On the other hand, it's not totally satisfactory that players are producing are choosing their quantities. They're really more often in things like Coke and Pepsi, they're setting the price, not how many cans of the stuff do they put onto the shelf. So this was a sort of a paradox in game theory for a number of years, for hundreds of years, and it's again, as I said earlier, it's what is the right model for the right type of markets. But the key thing is that this can be resolved to some extent. The Bertrand paradox can be resolved by considering the goods as substitutable or differentiated. In other words, Coke and Pepsi are similar. People who like Coca-Cola like Pepsi, but they're not identical. And similarly, you can have different types of crude oil. And so all of that is a build-up to say is actually the models that make sense for both Bertrand and for mean field games is that there is a customer preference for goods. And so even if your price is higher than mine, you will still receive some demand. Some people will still buy from you. And as we'll see, now a continuum mean field game model makes sense, at least in this linear case that I'm going to talk about, for both Cournot and Bertrand, and they turn out to be the same. So here is the basis of markets with substitutable goods. So again, there's n players, and the price that player I receives for his or her good in the Cournot competition is given by 1 minus the quantity he or she produces minus some interaction parameter epsilon times the average of the quantities produced by all of the other players. Okay, so here what happens is that this epsilon, which gets divided by an n minus 1, this thing is not, there is a differentiation. In other words, before I had 1 minus the total quantity, but here with this epsilon being less than n minus 1, then the goods are substitutable or non-homogeneous. That's the key feature. But the thing you also see is that the price is different for each player as long as this epsilon is less than n minus 1. And so you have a model with substitutable goods in which each player receives a different price, which is a function of his production and the production of everybody else. The interaction is by construction through the average, so this is the mean field type situation, meaning, as far as I'm concerned, I depend on any two of your quantities, but if I switch your identity, the interaction is still the same. So as far as you're concerned, as far as any one player is concerned, any other two players are exchangeable. That's the mean field structure, and that's what makes these things somewhat tractable. And then the other comment on this slide is that if I take epsilon equals to 0, then the players don't depend on each other, and the goods are independent. The price of mine is not dependent on the price of anybody else. And so that's the other extreme. When there is no competition, epsilon is equal to 0. So this is Cournot competition. This gives you price as a function of quantity, and then Bertrand is the inversion of that. So I want to, this gives you the vector of prices as a function of the quantities. This is a mean field type interaction. You can invert that system using something called the Sherman-Morrison formula, which you may be familiar with. And so this is where all these crazy functions come from, the inversion of that system. So if players 1 through n post prices P1 through Pn, the demands that each one gets are given by a linear system, which is given here with some coefficients which are given by these formulas here. And the only trick is that some of them may set a price which is too high. So you have to, I won't go through the details of all these slides, but the key thing is that some of the players, their price is going to be so high that they receive 0 demand, and there's a way of finding out how many players little n receive positive demand. But the main thing I want to, that I want to get from this is that the demand I, as a function of the vector of prices of all of the players, is of this form. It's A minus B, forget the subscript at the moment, Pi plus C times the average price of everybody else, which I'll put here. So here, the demand is linear. It's decreasing in my price, and it's increasing in the average price of everybody else. So if you put your price up, my demand goes up. If I put my price up, my demand goes down. And then the only thing is that these coefficients, which have some meaning, these come from the inversion of that previous system, and but they're known to us, and they depend on how many players are playing. So out of all of this, the Bertrand system is described by some linear, linear function of the prices, and then it's natural now to see what happens as n goes to infinity, and wherever you see here, sort of a little n divided by big N. Little n divided by big N is the fraction of players who are playing. This becomes the continuum variable. So now there's a continuum of players indexed by eta, which is between 0 and 1. And this is the proportion of players who receive positive demand. This is the continuum variable. And then the demand function of one of these players who sets a price P is again of this form. It's linear, decreasing in his price, increasing in the average price of everybody else. And the limit of those coefficients are given by some formulas which are given down here. Okay? And so the actual demand received by this player is this function d of his price and the average price of everybody else. It's linear in this way with these coefficients. And if this thing, if this thing is positive, that's actually what he gets. Otherwise, it's equal to 0. So the upshot is that there is some function d of P and P bar, a function of my price and the average price of everybody else, which describes as a fraction of how many players are receiving positive demand, the demand I get for my good. And so That's the model. All of that is just to set up what the Bertrand model is when there's a continuum of players and there's a linear demand structure. And now, what is the what is the dynamic game that we're interested in? So, any questions before I move on to that, please? Yes, Jonathan.
So what was DNN? Is it capital N is equal to small?
Yeah, no, that is, yeah, so I'm skipping a little bit, but what you have to do is you have to say, everybody give a price, okay? Let's say there's 30 of us in this room, okay? And then I compute, let's say for capital N, the prices that all 30 of us would get. But some of those are going to be negative, okay? So those people are actually going to get zero demand. So let's say I take out the one with the most negative or the highest price. Then there's 29 of us left. Then I have to recompute with n equals 29, and then I have to see how many of us get, and I have to keep doing that until I'm down to, let's say, given the prices that we posited, 17 of us have positive demand. So little n ultimately is going to be 17, and 13 are 0. So I skipped that step, but there is if we all post prices, and they're all high, then nobody's going to buy from any of us. Some of us will put low, some of us will put high, and that's what this little n is describing. And later on, that's going to be, yeah, and that's what this continuum variable is. Exactly, yes. So let's say I get down to 17, and the last player has positive demand, then it's 17 people who are it, But if I did 18, the 18th person will have negative demand, so it's not 18, I have to go down to 17. This is the recursion, yeah, that's right.
Constraint of addition for external?
Just that it's between 0 and I'm sorry?
Small n by capital N.
Oh yeah. Then after that, there's nothing on epsilon. There's nothing on. No, epsilon can be large, yeah, because the dividing by n has been gone into the average. So epsilon is greater than or equal to 0. No, I don't think so, because these formulas make sense for any epsilon. Nothing's blowing up, so I think it's fine. Yeah, there's no interaction. Yeah. Okay, so now here's the continuum version of this game. So now there is a continuum of players, and they're distinguished by how much of the good they have. So some are big players and some are small players, and they run out of this good. So X, in some sense, is labeling the players. This is the I, but it's also labeling how much reserves or capacity each of these firms have. So there's some initial density, let's say M of X. So that means there are players here who have a small amount of reserves, and there are players here who have a large amount of reserves, and most of the players are here. But when they run out of reserves, and everything I'm doing here so far is deterministic, when they hit 0, they're out of business. They've run out of reserves. If they're oil producers, they've run out of oil. If you think of this as booksellers, then they've run out of books or something like that. But essentially, in this thing, they're absorbed at 0. So they set prices, and depending on the prices they set, you can sort of anticipate the larger producers will can set lower prices. Then this density will move to the left, but at different speeds. So this may be moving at a large speed, this may be moving at a small speed, and when this mass goes through 0, the players are absorbed. So the number of players is diminishing. This is the exhaustible resources situation. So there's a continuum of players. At time t equals 0, the density of players is m of x. That's this graph here, where the integral is equal to 1. This distinguishes bigger and smaller players by their starting point. As time evolves, some players exhaust their reserves. So this density is m of t and x at time t positive, but the number of players, not counting the ones who have absorbed, may add up to less than 1. So eta of t is the fraction of active firms remaining. This is the integral of the density, but not counting the absorption at 0. That's what this plus means. And in general, this thing may lose mass. This is players, escaping the market because they've run out of oil. This is the situation which kind of makes the problem complicated. So what do each of the players have? So the players have reserves xt, which in general may be stochastic. A lot of the things I'll do will be deterministic. And their reserves go down at some rate q, and there's some fluctuation with some Brownian motion. For each player, this Brownian motion is independent. So this is the representative player who starts at initial point x. And the q is that demand function as a function of his price and the average price of everybody else. So that ABC function that we had before, that's what goes into the drift here. So he chooses P of t, but every player chooses something. So there's an average price as well. And depending on his price and the average price, this is the demand that he gets for his good. And then his reserves decline at that rate. And then there may be some Brownian fluctuation, but I'll skip that for most of the talk. So this is the dynamics of the model. And the dynamic version of the Bertrand competition is that he's choosing the price to maximize the expected lifetime profit. So this, as long as he has reserves left, is to maximize. So there's some discount rate R, which discounts future profits. So you like current profits more than future profits. He maximizes the price times the quantity. The quantity or the demand is given by this function here. He can only do this, of course, as long as he has reserves left. After he runs out of reserves, he cannot play anymore. And so and now you can see this is all set up for dynamic programming because this is a value function, u of t and x. And then skipping a lot of the stochastic control, but it's more than stochastic control because the average of the, because the law of this process is involved. Then there is a HJB equation associated with this, and that's given here. So I won't go into the details of all of this, but there is some Hamilton-Jacobi-Bellman equation that this U equation satisfies. But this U equation, has coefficients which depend on, well, there are things that depend on the average. There are things that depend on this fraction of players that are left. And so I need this m of t and x function as well. So this is one equation, but it does not sit by itself because there is that m of t and x function that is going into this thing. The other thing I want to point out is that if you look at just this kind of internal problem here, this is quantity times price minus du dx. This is where the s variable was before. So this du dx, the slope of the value function, is sometimes called the scarcity cost or the shadow cost. So basically, the bigger the du dx, the bigger the effective cost of the finite resources for the player at location x. I'll come back to that when you see the pictures. So just to, without doing all the mathematical details, there is some HJB equation associated with this value function. You know that if you solve the HJB equation, then that also gives you the maximizing strategy. So if you solve this is a quadratic maximization problem. If you solve that, then you get what to produce, not what to produce, what price to set as a function of the gradient of the value function, as a function of this eta. So there's a recipe, there's a formula that if you solve that equation, you can, you get the optimal price to set in feedback form. You can plug that in, and this is what the HJB becomes here. But you see also that this is not an equation by itself because you have the average price. The average price is the integral of the price that everybody sets with respect to the normalized density of all the people who are left. You don't count the people who have been absorbed at zero, so that's why you divide by this eta of t. But you need another equation, and the other equation is the equation for the density, and this is the Kolmogorov equation. So you know the initial density is m of x. The m is the density of the law of this process, this stochastic differential equation, whose drift is a function of this du dx. So it's all coupled in a weird way, but essentially the upshot is there's an HJB equation, there's a Kolmogorov equation. The m appears in this equation through the p bar and the eta. The u appears in this equation, for example, here. And the final twist is that the u equation, if you have time here going upwards, then the u equation is a backwards equation. You have to sort of solve it backwards in time. and the M equation is a forward in time equation. So the pro is that there's two equations, right? Not one player, not one for each player. So if there's 10 players, there's still two equations. I'll tell you what 10 means in terms of the continuum a little bit later. But the con is that the U is going in one direction and the M is going in the other direction. So numerically, potentially that could be something that is more challenging. Okay, so the upshot is that you have these two equations. And just as a digression, this mean field game theory, has been around for 10 years, and there's a lot of activity in it, mainly French. Here are some of the sort of, how these things are characterized. So there is a recent paper by Graeber and Massousson, which explains, I'm taking this from them, that much of the PDE-based analysis of mean field games is dealing with PDEs of this form. So abstractly, there are two equations. One is a AJB and one is a Kolmogorov. And the AJB is an equation of this form. There's a Hamiltonian here, which depends locally on dVdx. And then there is some operator which depends on, for example, this bracket means the integral of M. Okay? So the M equation, the M enters in this way, and it's non-local because it may depend on the integral of the M. And then typically the V enters the M equation through this coefficient here. In our case, the oligopoly model, the equation that we had before, the coupling is a little bit different. So the non-local part appears in the Hamiltonian, and there is a non-local part in the Fokker-Planck or the Kolmogorov equation. So a lot of the literature, most of the literature, does not apply to our situation, which is given down here. And the reason for that is that in most models that that are considered in that literature, the interaction of the players is through the X, through the mean of the state. So in other words, I depend on you as a function of where you are. But in these oligopoly models, these game theory models, it is through interaction of the controls. I depend on you through what you're doing, how much you're producing, or what prices you are setting. And so that's why the system of equations is different. I mean, they're both complicated, but that's the kind of the main reason for it. I'll skip this. The other thing is that this x equals 0 boundary condition that people are disappearing from the market, which is running out of reserves, running out of oil, etc. This is, makes the problem a lot more complicated. So often in the mean field games literature, and you may think this when you were, if you're familiar with control, you may think that at the end of the day it's kind of a linear quadratic problem, and a lot of the examples that exist in mean field game where there is a solution are of linear quadratic type. The answer is a quadratic function essentially, and that's not true here because of this boundary condition when x is equal to 0. So that's the main difference. Okay, so what can we say about analyzing these equations? So there are two things that there are two ways that I want to look at it. One is in the case when this epsilon, this interaction parameter, is relatively small, and second, when we can do numerical solutions of these two equations. So it's natural to look at these equations when the interaction between the players is small, meaning close to 0. And so let's look first at the case when epsilon is equal to 0. So there is still all of these players that you have here. They're still moving to the left. They're still getting absorbed at 0. But the demand that this guy gets doesn't depend on this guy. But they're all there, but they're kind of monopolists in their own market. So when epsilon is equal to 0, the equations simplify a little bit. So I'm going to call u0 and m0 the value function of a representative player and the density of the players when epsilon is equal to 0. Then the m now does not appear in the AJB equation because I don't depend on u, so I don't have to keep track of the density. So you're left here with an equation of this form, and this equation is essentially a time-independent. You can find the time-independent solution of this, and you can get an explicit formula for the value function in this case. It depends on the lambda w function, which is the inverse function of z e to the z. But anyway, there's some formula for this which is given here. The pictures will come in a second. Those will be more instructive. You can get what the dynamics are in terms of this lambda w function, how the trajectories evolve over time. You can recover for this continuum mean field game a thing called Hoteling's rule, which is that the gradient of the value function evaluated along the optimal trajectory grows at the discount rate. This is something that economists know for the one-player game, and this is the continuum mean field game version of this. And you can get the dynamics of the price. I'll skip that. And finally, you can get, in closed form, the exit time. So for a player starting at location X, so this is a player starting at location X, how long in this deterministic game does it take him to run out of oil? And this is given by a formula that is given down here. Okay, so all of these things you'll see pictures of in a second. And then for the density, now you have a Kolmogorov equation. But of course, for the Kolmogorov equation, the u enters into the drift of this equation. But you can solve this essentially explicitly, and you can compute the fraction of players who are left at time t. So remember, the players are still disappearing, even though they don't interact with each other, but they are disappearing at some rate that you can compute, which is given down here. So here are the pictures then. So the pictures are more instructive than the formulas. So you know, what do the value function, the density, etc., look like? So the first graph is u0 as a function of x. So you know, what you'll see in these games is that the value function is an increasing concave function of x. So the way to think about it is the game moves from right to left in the x variable. The players run out of oil or whatever it is, and so their slope gets steeper, which means their scarcity, you know, as they get closer to zero, their effective cost, which is du dx, gets larger. That's what you see here. Or another way of thinking about it is that if I give you an additional value of oil, an additional barrel of oil, the marginal value of that is less, the bigger you are as a player. So this is u of x in the monopoly situation. These are, you can't read it properly, but it's x of t as a function of t. Here we go, x of t. So depending on where you start, this is how you run out of oil. You don't go down at a constant rate. You decrease your rate of production as time goes on. Here is a graph of the tau of x, the exit time for the player who's starting at location x. Here is the eta 0 of t, meaning that at time t equals 0, this is a function of t, you know, you have 100% of the players left, and then you know, by the end of the game, by the time everyone has run out, then this is the fraction has gone to 0. This is the average price of the oil. It's increasing over time, and the quantity of oil produced is decreasing over time. So this is a simulation where you had an initial density which was a beta distribution or something like this. But this is just to get, you know, to kind of get the representation of how the game evolves over time. This is not a game yet. This is still the monopoly. So then the natural thing is to say, okay, in the regime that epsilon is small, close to 0, how does a small amount of interaction affect the game? So that means to look for an expansion of the value function whose first term is the monopoly u0, and which is corrected at some rate epsilon by some function u1. Similarly, the density has an expansion whose first term is that m0 that we just computed, plus some expansion proportional to epsilon, m1. So at first order, the 0th order, the ones with the 0 are the monopoly problem, and then the idea is to get the u1 and the m1. So again, I won't do all the calculations, but you can take those equations, expand them in epsilon, compare powers of epsilon, and get an equation for the u1 whose solution is given by some formula like this. And then one thing you can see immediately, not see immediately, but one thing you can check is that this u1 is non-positive, is negative for all t and x, which means that if you bring in other players, as you would expect, you know, if I have the market to myself, I will make u0, the value of my game is u0, but this u1 is negative. So as soon as you bring in competition, you reduce the value of the firm, which is what you would expect. Competition will reduce individual profits as you expect. That's natural. Then what happens to the density? So the 0th order is the one whose formula was given 2 slides ago. You again take the Kolmogorov equation and you look for an equation for the M1, which is given here, and you can solve this equation essentially by a formula which is given here. Now once you have these two things, then you have what the demand is for a given player up to order epsilon. This is given by some formula here, and so you get the demand. You know, I set my prices. If I'm a monopoly, this first term is the demand I would get, but it's corrected by this formula here, and this correction term is negative. So that means that you know, when you bring in competition, I produce at a lower rate than if I was by myself. So you'll see in the pictures that competition slows the game down. That because other people are there, the prices I set are such that the resources are conserved for a longer period of time. You'll see this in the pictures in a second. Yeah, here's the pictures. So this is x of t for different values of epsilon. So the blue is the monopoly. The lowest one is the monopoly. The purple one is epsilon is equal to 0.2. The green one is epsilon is equal to 0.5. So you can see that, you know, when you have competition, then you produce at a slower rate and the game goes on for longer, just at least in this deterministic situation. Okay, so that's something, and there are other things that you can see that from doing this expansion in epsilon. And then if epsilon is not so small, if you really want serious competition between the players, then you will be looking at solving these equations numerically. And so as I've mentioned, you know, solving the system that you would get if you had a finite number n players, even 2 players, is very difficult. And I keep stressing that because I think I spent 5 summers in a row saying to myself, this is the summer in which the code is going to be robust and be able to solve any of these games, and it never happened. You can solve it in certain situations, but you know, you know, it's never so satisfactory that you can vary the parameters and, you know, get a good code working out of it. For many years, a co-author of mine would give talks, often where there were kind of numerical applied math people, and he would talk about the difficulty of solving this system of equations, and there would be experts in numerical PD in the audience, and they wouldn't believe him, so you know, they would say, oh, come on, it's not so difficult, send me the equations and I'll send you back the code. And so you would send them the equations and then you would never hear from them again. So it's genuinely difficult, I think, and so this mean field game stuff is needed to you know, to even to be able to say anything heuristically about, let alone quantitatively, about any of these problems. That's why I keep stressing this. So in the, you know, there are difficulties, of course, with this equation, the mean field game equations. One is backward, one is forward, et cetera, et cetera. You may also want to mimic the case where the initial density of the players is a series of Dirac functions or of point masses. And so I won't go through the numerical details, but one thing that is useful is to solve not the M equation, but for the integral of M, the tail distribution function, eta bar the integral of M starting at the point X. And so this satisfies some equation, and this equation is typically more amenable to numerical treatment. That's just a comment. So I'll skip the numerical method, and you know, here are some things that you can see. So for example, this is the average price. So here now I compare the monopoly, and epsilon is equal to 0.3, and this is the average price. This is the fraction of players as a function of time. You can see that they run out of oil slower when there is competition. Here are the trajectories. Here's the total production. So I've skipped a lot in the interest of time, but you know, numerically, at least for relatively moderate values of epsilon, these two equations are tractable. Even though you have a forward-backward, there is a good numerical method for being able to deal with these things. Okay, and then the final thing that you might do is to say, well, you know, because I started off saying it's erased, but there is a, you know, a small number of large players, but now I have a continuum, so there's a large number of infinitesimal players. So it kind of looks like you're going opposite in philosophy to what you want. So to try and resolve those, you may say, okay, well, I really have you know, a player over here, and I have a player over here, and I have a player over here, and make these you know, Dirac deltas, make the initial density you know, well-separated Dirac masses. And in the deterministic case, this is fine. In the stochastic case, of course, eventually they will blur. So suppose instead I have an n-player game, and I go to the continuum mean field approximation, but I represent these players with a Dirac mass centered at whatever their initial reserve level is. So it's a series of Dirac functions adding up to 1. So for example, if you had 4 firms with initial capacities or reserves 1, 2, 3, and 4, then this would be the integral. This would be the integral of this m. This would be the eta function. This would just be a step function, because like I said here, yeah, that's what I forgot to say. Here, you know, to handle the case where the initial condition is a series of delta masses, that you cannot do numerically, but when you do this integral, this becomes a step function that's given here. And so this would be the initial condition for that eta bar equation. And so again, you can do this, you know, here's what you get from the numerical solution when you had 10 players. And you can see, of course, this is, you know, these jaggedness, this is not numerical, this is what you want. This is when players exit the market. These are discrete events because this whole bunch of players go out, and that leads to a jaggedness in the average equation. So this is really what you want to see. So you can approximate, in some situations, the finite number of players. And then finally, okay, so I haven't said anything about convergence approximation. There is a theory, you know, the error is like 1 over n. You know, there are certain things you can say, but, you know, perhaps you want to, you know, what can you compare? So here's a comparison. So even for the n-player game, there's no explicit solution. There is approximations in the limit of small epsilon. So what this picture is showing, maybe it's not quite fair, is that I'm comparing the mean field game approximation with an infinite number of players to an approximation to the solution for 2-player games. So I'm comparing 2 approximations, not an approximation with something that's exact. But so I have 2 players. One is large, he starts at 0.75. One is small, he starts at 0.25. And these graphs are the trajectories of the small player and the large player respectively. So the blue, the bottom curve, is the monopoly. The green, or whatever color that is the approximation to the exact 2-player equations, and the purple is the mean field game, is the numerical solution of the mean field game with the Dirac masses at 0.75 and 0.25. And so the point I'm trying to make is that obviously I'm comparing 2 approximations, but at least qualitatively they look the same. So in other words, we're trying to approximate a 2-player game with an infinite number of players, but at least in the situations that we've tested, you know, the quantitative results are fairly similar. It's not like we're getting some completely different equilibrium that is different from what you would get if you actually tackled a 2-player game. So it's an approximation, but you know, at least it seems to preserve the main features, at least as far as we've tested, of the game that you're trying to approximate. Okay, so let me sort of wrap up, and happy for questions. So, you know, there's a lot of things in this kind of project that I haven't talked about. I was mainly trying to describe the situation and from the point of view of if this mean field game type model is new to most people here. One thing is to go back and understand stochastics. So I had on this board here before economics, and I had finance here. And in finance, you know, the whole point of writing a stochastic model for the price is that we don't know, we're not trying to understand who's buying and who's selling. The price is just random in a statistical sense. It's phenomenological. You observe it. It's a time series. It has some statistical behavior. Now, when you go to the other end of the spectrum and you really are trying to understand or model at least what could be affecting price, it becomes a sort of a harder question to understand where the uncertainty is coming from. So I had here lazily, a lot of this literature kind of lazily puts a stochastic, where is it? Here. Add a sigma dw, because that's what we do in control systems, or that's what we do in finance. But this is not really the source of randomness in commodity markets or in energy markets. It's not fluctuating supply. I mean, so for most of the pictures and the results I showed you, the sigma was 0. I didn't have the Brownian. So where does the uncertainty come from? So one source of uncertainty is which way am I going? This way is China, is demand. All of the models that I had were of the form 1 minus quantity, but this demand curve is stochastic for various reasons that I won't go into here. And so there's a case for replacing this 1 by a stochastic process yt, for example, geometric Brownian motion or something like that. And that is to model the fact that there's a lot of uncertainty about what the demand is, whether it's to do with a slowdown in China or various other macroeconomic phenomenon. But mathematically, that leads to a continuum mean field game in a random environment. And that's also a little bit complicated that we're trying to understand, because the density is now a function of this new stochastic variable, and it's not quite clear how to tackle that. But games with stochastic demand is something that is of very great interest within this type of model. The other thing is that oil prices, at least over short time scales, are extremely volatile. And within this type of model of exhaustible resource, it probably makes sense to have an inverse demand function. So remember, that's price as a function of quantity. So I had linear, basically. And you may want to have one which has an infinite choke price. The choke price is the price that you get if the quantity goes to 0. And so instead of having 1 minus q, there are models we understand, at least in the homogeneous Kuno case, where you have q to a power. And if this power is bigger than 1, then you have an infinite choke price. So the case that we just did is rho equals 0, the linear case. And so within this so-called power or constant prudence family of inverse demand functions, we understand the Nash equilibrium in the static game. We can prove various things about the existence and uniqueness of the Nash equilibrium. But what has to be worked out, which is sort of in progress, is if you have substitutable goods, what is the right formation of this type of model? This is really for homogeneous goods, but when you have goods which are different, what is the right prescription for these inverse demand functions with infinite choke? And then the final thing, obviously, that we would like to get is, having done that, is to incorporate that with stochastic demand and then see if you can capture some of the volatility that we see. Okay, so I'll stop there. Thank you.
Finishing with uncertain demand. So during the static game, this is not so well. So I was just thinking, how does it go back to the original correlation, which is anyway analytically very, very hard? Is a simulation strategy possible to get a better idea about the solution, at least in relation?
So because there's an optimization involved, and because there's an equilibrium involved, it's inherently, a nonlinear problem. In other words, if you bring in randomness, this may disturb your uniqueness of Nash equilibrium. You could have multiple equilibrium, et cetera, et cetera. So I think for these problems, because of optimization and equilibrium, you cannot sort of start with, to try and simulate the Nash equilibrium is so difficult anyway. No. Okay.
It may not repeat.
Right.
I'm just saying, so in the system itself.
Yes, so the only thing there is then that you have to solve the optimization problem of each player. And then you have to interact your best response to me, my best response to you. So even in the very simplest things, that can be complicated because if there's multiple...
At least the numbers will be fixed.
It could, yeah. But if you have multiple equilibria, it may not converge because of the jump between equilibria. So it's possible if it's a good clean solution, if there is really a nice unique solution to do that. You could also, yes, you could simulate the system in the following way. You could say that you have 10 barrels, I have 8, we play against each other, you go down to 7, I go down to 4, and then we could see what happens. Yeah, so we could do a discrete.
So you generate successive chains and some of them will be replicated.
Right. So it will grow, the complexity will grow very highly in the number of players, but we could get something in the small number of players. So,
That is not. As it is, this is just so hard.
yeah. So it's possible we could do something like that for small number of players.
Other questions? So you had mentioned like the new representation part, it's hard to replicate, but so what is the exact problem? Is that imposed or?
No, I think it's well, so you have a system of equations. So for example, let's say you have two players. You have V1 of x1, x2, V2 of x1, x2. Right? These will satisfy a coupled system of PDEs. Right? So in the V1 equation, you'll have derivatives of the V2 and the V2. Now, of course, you have that in fluid dynamics and everything else. But I think the Nash equilibrium thing is that the interaction is very, how should I say, it's very coupled. In other words, how I appear in your equation, it really affects the character of the equation. So it's not so much that it's, so there's no theory. I mean, it's system of partial differential equation, there's no viscosity theory, there's hardly anything, right? In zero-sum games, you have a theory because there's only one equation, you have viscosity solutions, etc. When there's n equations, there is not much theory. So I think it's just the coupling of the systems is very complicated. On the other hand, what we're describing is not that complicated. I mean, for example, you can simulate the game. So you have some oil, I have some oil, we play, then we move, then we play again, then we move. So there's every reason to believe that it's not difficult because it's ill-posed. So when I say it's difficult, I mean for certain parameter values you can solve it. But you have to add, for example, noise, you have to do some very non-uniform grids. Then you change the parameter values for me, and then I have to restart again and do it. So it's just hard to get a robust, to get a satisfactory code. That doesn't mean, I don't mean you can't do it at all, but just in a way that you would consider robust, satisfactory black box. This isn't there. And of course, when you go beyond 2, then you have the problem you always have with PDEs, that's the curse of dimensionality. So if you're talking about 10, it's in 10 dimensions, you can't do much anyway. So there is a case for the continuum approximation even there, even if we could do this for 2 players. Okay.
Is it possible to include another term like why just the Brown motion? Like can you just include a Levy process or something like that?
Yeah. So in the Minfu games, you have it's a limit of n players with n independent sources, and then there has to be a law of large numbers, and then you get a representative process, with a single Brownian motion. So the noise source, yes, you can change it as long as you can do. Yes, I mean as long as you have this. So in other models, we have a Poisson process here, and a Poisson process means you suddenly discover oil, right? So you jump up. Now so I was trying to say that the choice of randomness needs more thought in economics than maybe it does in finance, because in finance you introduce a large class of processes and then you try and estimate parameters or something like this. Here, what is causing the randomness? So one source of randomness that drives prices of oil down is that there's a new discovery, so there's new supply. So you can put a Poisson, but yes, you can put Levy process, etc. So, for example, in the kind of the theoretical mean field game literature, they haven't got to this yet because they're still developing all this kind of thing. But there's definitely reasons why you might want to put jumps here from for different, for various different applications. And I haven't seen that done except for these jumps for different values of all. But I think that needs to be done. Yeah. Okay, thank you. Oh, okay. Thank you very much. Okay, thank you. Thank you very much. My pleasure. Okay.